Howdy, everyone. We'll get ready. Or get started, whatever I want to say. So welcome to another review session. Sorry that there was none last week. And then in terms of the practice problems, I'm going to catch up with everything that I've missed this weekend. So you should get like 3 new sets of practice problems if you do those each week. So that'll help you for your exam coming up soon. So you can go back and review any of those once those are posted. I think that's all the information I really have at the moment. Are there any questions for me before we get started on just like class stuff? Yeah.
So for the last chapter we just did,
Mhm.
there's gonna be practice problems for those.
Yes, yeah. I'll post like last week there was no review session and I didn't post practice problems, but I'll post practice problems for that on this weekend.
And also remember the pre-recorded lecture.
I can do a little bit of note stuff if that would be helpful to go over it. I'll probably have time this weekend to do that. Yeah. I think I could also probably find an old video and link that too. I'll look through what I have. Any other questions? Cool. Okay, what do we want to see today? Questions do we have? Anything?
You have access to the quiz from yesterday.
Yes, I don't know if I'm allowed to go over the quiz yet. I think there's still people that are taking it. But if you have a topic from the quiz, I can do that.
You could go over like the difference between like the rate laws and rate up and decay.
Yeah, absolutely. So in terms of like integrated rate law and stuff.
Like, because I noticed it was like different, like because it was like logarithms and then the inverse.
Mhm.
It was like different for half-lives.
Yes, yes, okay. So when we talk about rate orders, right, there are 3 that we focus on. What are the 3 that we focus on? Good, right, so we have 0th, first, and second orders. All right, and this tells you how the rate of the reaction changes with respect to concentration. Okay. So if we have a 0th order reaction, how does concentration, what is the concentration dependency for 0th order? Right, if concentration doubles, what happens to rate? It stays the same, right? So 0th order means that there is no order or there's no correlation between the rate and the concentration of that reactant. It doesn't matter if you have 1 molecule or a mole of molecules, the reaction will proceed exactly as it is proceeding, right? You can't make it go any faster by increasing the rate or by increasing the concentration of that reactant. Okay. So what does that mean for first order? If the concentration doubles, what happens to rate? It also doubles. Right, so this is a 1-to-1 respect for concentration to rate of reaction. So if you double your concentration of that reactant, you're going to double the rate of that reaction as well. So if it's going at 2 molarity per second, now it's going at 4 molarity per second when you double it. So concentration and rate increase the same. And then for second order, if concentration doubles, rate does what? Times 4, right? Rate quadruples. So this is a 1 to 2 or a square of that concentration. So concentration increase causes rate to increase more. We'll call it. All right, so if you double your concentration, your rate is going to increase by 4. So we're increasing it even more than what we increased our concentration by. Okay, so something a second order, then just a little bit more of that reactant will cause the rate to go even faster. Right, or a lot time faster than just a little bit more. Okay. This is the general breakdown of that. How this shows us that it's happening is with our straight line plots. So if we have time on our x-axis, then the straight line plot is going to be concentration, the ln of concentration, and then 1 over concentration. This is for 0th, first, and second order. And when we talk about a straight line plot, we're talking about the slope of that line. So what does a time versus concentration plot look like for 0th order if that is going to be straight line? Do we have a negative or positive slope? We have a negative slope. And where does that come from? Does anyone remember what the 0th order like integrated rate law is? Yep, right. So we have a negative k for that. Let me look to see if I can find
Is that graph supposed to be denoting the reactants?
It's denoting the rate of the reaction.
So it doesn't matter like what direction it's going in?
Correct. Right. It will always, so 4 is right, 4 0th, first and second. So as we'll just go through this, right? What should the negative or what should the line be for first order? Negative or positive slope? That one's also negative. And what about second order? That's positive. Right. So all 0th order reactions will always have a negative slope. It might be something that looks like this, might be something that looks like this. I'll change that color, right? It might have a different slope for it, but it'll always be a negative slope. Same for first order and same for second order. It'll always be a positive slope.
So it was always a negative and always a positive?
The slope of the line for first and second, or for 0th, first and second. So for 0th and first order, it'll always have a negative slope if it's one of those orders. And if it is a second order, it'll always be a positive slope. For your quiz preview page, but I can't find that right now. That's fine. Right, and so this is showing you the change in concentration. So as your concentration changes over time, this is what's happening to it. So that's what it means by the first, by the straight line plot. So for your first order, right, your integrated rate law looks like ln of a t equal to negative kt plus ln of a0. So the slope, right, this is in y is equal to mx plus b form. So your slope is always going to be that negative k or that rate constant in the negative version of that. Okay, your second order is 1 over AT equal to KT plus 1 over A0, right? Where A0 is your initial concentration and AT is going to be at some time point T. Okay, and then your first order should just be the concentration of AT equal to negative KT plus A0. And all of these are given to you. You just need to know which one is with each order. So if it says like, oh, a first order reaction, you know to look at the ln version.
Are these formulas derived?
So if you start at the 0th order and then you take the derivative or the integral derivative, then you get the ln version. And then if you take the derivative of the first order, then you get the second order reaction. So you don't need to know how to take those, but that's what happens if you do them. Right, and that is to get the straight line plot version of that graph. So if it's a first order reaction, then if you were to plot all of those concentrations that you have for change over time, right, if you plotted it as A over T for first order, then your reaction might look like this, right? So that's not a straight line. But then if you did ln of A over T, then you get your straight line there. So you know that it's a first order that way. So you can determine the order experimentally, which you should do in lab at some point if you haven't done that already. Has everyone done that lab yet? No? Okay. So you should do that in lab at some point. You'll see a reaction and I think it's based on color or something. But you'll take time points and then you'll graph it. And then you can take, right, concentration of A over T, ln of A versus T, and then 1 over your concentration versus T, and you'll find which one is the straight line based off of the graphs that you do.
So it has to, so when we're trying to determine which order it is, it's always going to be the one that's linear.
Always the one that's
So
linear.
if it has a curve, it's not that one.
It's not that one, right? So if I would say which order is this reaction, whatever it was, you would tell me it's first because the straight line plot is for the first order reaction that it correlates to. Does that make sense how you determine it by graph? If you're not determining it by graph, it would tell you this is a second order reaction or this is a first order reaction. Okay, any other questions with that? That's a great question. So everything with your integrated rate laws, all of them have to have this K version here, or this K here. This K comes from your rate law. Does anyone know the general like formula for a rate law? Right, we have rate is equal to times the concentration of A, right? In its simplest form, That is your rate law. So this K here corresponds to, right, this K, or this K, depending on what the order is. Does anyone know what units of rate are usually in?
Molarity per second.
Usually molarity per second. It's usually a concentration divided by a time. So usually it's big M divided by seconds. It could be micromolar per minute. It could be, some other form of concentration, molality per hour. I don't know. But it's usually molarity per second. What unit is concentration in? Usually in molarity. This means that K is always changing, right? The units for K are variable. And it depends on the order that it is. So if we have a first order reaction, or I guess if we have a 0th order reaction, we'll just go in order. If we have rate is equal to K times concentration of A, where does the order go? It's the exponent. So if we have a 0th order, right, it means we have an exponent of 0. So what does the concentration of A turn into? 1. So this means that the rate law is rate is equal to K. Right, it's only dependent on the rate constant. So if the rate units have to be molarity over second, what do the units of K have to be? They also have to be molarity over second. Do we see why that is the case? If we have a first order reaction, we have rate is equal to K times the concentration of A. Whereas what is our exponent now? Just 1. So that just means that rate is equal to K times concentration. If rate is still in molarity over seconds, do we have a molarity component in the right-hand side of our equation? We do, right? We have molarity here. So what do our units of K have to be? 1 over seconds. Right, K is 1 over seconds for any first order reaction. So what does that mean for second order? What do you think it has to be? Yes, yep. So if we have second order, then rate is equal to K times A squared. So then we have still molarity over seconds, but now we have molarity squared on top. So in order to get rid of one of those molarity squareds, or to get one of those molarities, we need 1 over molarity times second in our rate law units so that we cancel out a molarity, and then we're just left with molarity over seconds. So a shortcut, if you want to use that, is that your K units are 1 divided by molarity to the overall rate law, or overall rate order, minus 1 times seconds. Oh, you can't read that at all. So overall rate order minus 1 times seconds. What does this mean, right? If we had second order, that means that our units on K, 1 over molarity our overall rate law, our overall rate order is 2. 2 minus 1 times seconds, which equals 1 over molarity times seconds. Does that match what we predicted from the above? It does, right? So this matches. And that works for all of them, right? If you had first order, then it's 1 minus 1, which is 0, which turns into 1. So that means it's just 1 over seconds. And then if it's 0th order, you have 0 minus 1, which means that you have molarity to the minus 1 in a fraction, which means you have to flip it to the top. So that turns into just molarity over seconds, right? So it all matches that way. So if you need the units on K and you have something where your rate is K times A squared B C to the third, right? What are your units on K? Well, what's our overall rate order here? Yep. What are your units on K? Perfect. Does that help your question? Yeah.
So for that one, that's rate order 6. What would the formula look like for that one?
For like integrated rate law, you didn't need to know that. That's a lot of derivatives that I don't remember how to do anymore.
We won't get like quizzed over that or?
No, you could do an overall rate law that's more than 6 for just like writing the rate law purposes of it. But in terms of like straight line plots, half-lives and all that stuff, it's just 0th first or second. I think if I remember correctly, you honestly just add an exponent to the concentration component. So it's like third orders something happens with this KT component here, but this is just getting an exponent bigger. So this would look different, but I don't remember how to do that.
Do I remember them mentioning like specifically the rate order was greater than 2, or was like something you could do?
Yeah, but you won't be quizzed on it. Yeah. This is just in terms of like, do you understand what happens with it, with the K and the rate constant kind of thing? Or could you solve for it that way? Okay, questions there. Okay, so then the other thing we can talk about with integrated rate laws is, right, if you have your 0th order, your integrated rate law is your concentration of AT equal to KT plus A0. So if you were to talk about a half-life, does anyone know what a half-life, what does that mean? Yep. Right, so time it takes for the concentration to go down by half, or for half of that initial concentration to remain. So you can always use, if you like don't remember which half-life formula goes with which thing, you can always use your integrated rate law, and you're just going to plug in T1/2 for T, right? So they're saying, okay, AT is, or it's T1/2 at this point now, is K T1/2 plus A0. You just plug in what that half-life is, what that time is. If you want to use numbers, you always start off with 100%, right? So you're going to start off with 1 here. So at T1/2, you have 0.5 left over for your remaining concentration. Yeah. It should be, yes, sorry. Yep, it should be negative for 0.
When you wrote the A with the T1/2, is that like the concentration denoted as after the halftime?
Yep.
Or half-life?
Right, what that concentration would be after that half-life. So if you started with 100 as your concentration, then you would plug in 50, right? Whatever it is for half of that initial concentration. Right, so if you solved for T1/2, then you have 1/2. Sorry, you have T1/2 is K and then 0.5. So this goes to T1/2 is equal to 0.5 over K. And that should be on your formula sheet as well.
And the K that we're solving for, it's the same one from the integrated created law formula?
Yep. So that K all corresponds to the same reaction. Okay, and then that would be the same as your formula. So if you just plug it in, you're like, oh, that's the one I'm using there. Good to go.
What is the units for half-life?
It would be the same units as whatever order that is still in, right? So T1/2, if you're solving for the time it takes, it's that time component. So usually seconds, minutes, something like that. But K would still be molarity over seconds. That keeps the same units that we talked about back up here. Okay. Your first order reactions. This is all of your radioactive decay. So anything that is radioactive or some sort of isotope decay, something like that, all of that will be first order. So you can, even if it doesn't tell you if it's first order in the reaction or in the question, if it tells you that it is a radioactive decay, you automatically know it's a first order reaction. And then this one, T1/2, is the ln of 2 divided by K. Or I think this is 0.693 over K. And you never need to solve this and solve in terms like, what is this formula? That will be given to you. You just need to recognize which one it is on your formula sheet. And then second order, right, that was 1 over AT equal to, this one's positive. So for this one's actually 1 over 0.5 equal to KT1/2 plus 1 over 1. So this is 2 equal to K T1/2 equal to 1 or plus 1. So this is 1 over K is equal to T1/2. Notice how all of your half-lives come out to a positive K, right? There's no negatives in it because you can't have negative time. Any questions? Does that help answer your initial questions with all of those? Do you want to do a little bit of practice with these?
I do have like one.
Yeah.
This is kind of more conceptual.
Mhm.
But so we just talked about like the different rate laws and stuff with the different orders. Like how come like the actual like observed stuff we see, how come they're not all just one order? Why are there varying orders?
In terms of like how one reaction can be first and one reaction can be second. I think that has to deal with how many molecules are coming in contact at a time, right? And it has to do with the reaction mechanisms, right? So sometimes a reactant will not get used until the other reactant it's supposed to be reacting with goes through some other changes, right? So it has to go through an intermediate, an activated complex, and once it gets to that specific section, then that first reaction can come in, right? So, or that first reactant can come in and react with it. It's not always going to be 1-to-1 because not all collisions are perfect. And not all of them are used at the same time. Does that kind of answer your question?
So like, you said that like there's a sequence to it, so does that mean like zeroth order, first order, second order, they happen like consecutively, or?
No, it's just in terms of a sequence, in terms of like steps that need to happen for the reaction to happen. It doesn't necessarily, it could be a second order reaction and then a zeroth order, then a first. Does that help? Cool. Okay. Okay, so okay, so this one doesn't necessarily involve a integrated rate law, but just to get you started thinking about half-lives and what it means to be a half-life. We said OS 182 has a half-life of 21.5 hours. And how many grams of a 10-gram sample would have decayed after exactly 3 half-lives? All right, so what's the easiest way to do this one? Yeah. Yep. All right, so this one you can just say, okay, I'm going through 3 half-lives. Let me divide 3 times. So we originally start with 10.0 grams. If we go through 1 half-life, then we end up with how many? 5. If we go through another half-life, how much do we end up with? 2.5. And you end up with another half-life. How much you end up with? 1.25. Okay. So you would end up with 1.25 grams for this one. I always like to show one of these like this, just so that you could also do this to check your answer. So if you use an integrated rate law and you're like, oh, you know, my T1 half or whatever it is, it's gone through 4 half-lives, you can kind of fudge some numbers to see, does this make sense, right? If I have, right, if it's gone through only, we'll say 40 hours, right? It's been decaying for 40 hours. Where does 40 hours fall with you on your half-life timeline? somewhere between 1 and 2, but it's pretty close to that second half-life, right? So if we're close to that second half-life, that means that we should be at about 2.5. So our answer that we get should be close to 2.5. If you don't have 2.5, then like go back and look at your math again, right? But it's always good to just like break down a half-life quickly just to see, am I on the right track? Does my answer make sense?
And breaking it down like that works for all different orders.
Yep, because every time doesn't matter for 0, first, or second order, your half-life is still a half-life. It still means that you have 50% left than the original. Okay. Any questions on that?
Same answer plugged into the half-life equation for first order?
I think you should. Yeah, and so then you can also check it that way as well. But for half-life, it's pretty easy to have a way to check your answer. Okay, so for this one, we have a radioactive isotope has a half-life of 3.5 hours. How many hours would it take for 33% of the sample to remain? Do you want to walk through this together or try it on your own? Try it. Okay, I'll give you like a minute or two to try it and we'll start talking about it in case you get stuck. What was the first thing we need to do for this question? If anyone's stuck on how to start. Yep, so you do need to solve for K. Because we are given T1/2, but then we're asked for how long, right? So we're given a time component, but then asked for another time component. So in order to answer that second part of the question, we need to use our full integrated rate law. So we need to use the T1/2 or that half-life formula to get K so that we can then use that in our next part of the question. I got K equal to 0.198. What are our units on K? 1/2. 1/hour here. Yep. 1/time. Okay, and then what do we do once we have K? Yep, so then we can use it to solve for time. So then we can use our integrated rate law. So we have ln of A at time t is equal to negative kt plus ln at time 0. Do we know what our concentrations at time t and concentrations at 0 are? We could like make it up. So from our question, we know that 33% remains. So that can be whatever you want it to be. If 33% is better as starting off with 100 and you have 33 left, that's totally great. If you want to start with 1 and end up with 0.33, that's totally great. If you want to take a random number and take 33% of that and use that as your time t, that's also really great. But you just want 33% to remain. So it doesn't matter what your starting material is. For me, I like to use, if I have 33%, then I just change that to percentages. So I make 100% 1. So I say 0.33 remains. I know what my T or my K is. I just solve for that. And I have my ln of 1. And then T here. All right, we're solving for that T component. So I got T is equal to 5.6 hours. Do we agree with that? Okay, and then if we check that like we did our first question, right, we have 100%, we have 50%, we have 25%. Where is 33% in this? It's like pretty in the middle, right? Pretty in the middle here. So we have 3.5 hours here, and then another 3.5 hours would be a total of 7, but we only go through about half, right, of 3.5, which is 1.75. So that is half of that would be 5.25 total. So 5.6, pretty close to that, right? It takes a little bit longer to get to 33%. 33 is a little bit closer to 25 than it is 50. Okay, so that checks out. That makes sense.
How did you get a negative number.
So when you take the ln of 0.33 and subtract that from the ln of 1, it ends up negative. So if you do, which is also the same as ln of 0.33 divided by the ln of 1. I'm sorry, you could also do this.
Oh, this is the log rules, right?
Yeah, log rules. But this was ln of 0.33 minus ln of 1. Yeah. Which equals. Questions there on that one? Any other questions on half-life and anything? Does this make more sense? Yeah. Okay. Any other questions? How are we feeling about equilibrium stuff that we talked about in class today? Do you want to do a little bit of review of that? Sure. Anything else on half-lives? I won't stop if we want to have more questions. So the next thing we move into is equilibrium. And this is meaning that the rate of the forward is equal to the rate of the reverse reaction. So your concentrations of products and reactants are no longer changing, but that doesn't mean the reaction stops. The reaction is still happening in the forward reaction, still happening in the reverse reaction, but now the rates of that is the same. So your concentrations are no longer changing. So that's indicative of your forward and reverse reactions, or forward and reverse arrows. Okay. That's your equilibrium. We can show equilibrium with K. And what did we say K was? Products over reactants or reactants over products? Products over reactants. And this time with equilibrium, we can use the coefficients of our balanced equation in the equilibrium equation. So if we had what would we need to do if we have N2 and H2 forming NH3? What do we need to do first? We need to balance our equation. Does anyone know how you're going to balance this? Perfect. Yeah, I think that should be good. Okay, so if we're gonna write this as chemical equilibrium and as a K, what goes on top? Products, which is your concentration of NH3. Then what do we do with that 2? Square it. And then what do we do on the bottom? Reactants. So we have N2, and then we have H2 cubed. Okay.
I have a question.
Yep.
So when I asked the professor today about the coefficients we use, asked if it was like about like reaction order,
Mhm.
since we're still measuring like the change, and like reaction rates. And then, she said that like the thing represents like the reaction order and the coefficients. But she didn't really say whether or not you use either or.
So for a slow step of a reaction mechanism, and then the coefficients are used in your rate law, which corresponds to the rate order. That slow step can also be used in an equilibrium, and you can use those coefficients there. In terms of equilibrium, just as an overall general equation, those coefficients do not relate to the order of the reaction. You need to know the breakdown of those steps in order to determine what the rate law would be.
So the exponents we have there,
Yep,
they represent the reaction order?
they do not represent the reaction order. Because we don't know how N2 and H2 are breaking down and reacting to form NH3. We need those mechanism steps in order to determine what the actual slow step is, and therefore what the orders of those reactions are.
So does reaction order have like an effect on equilibrium?
Yes and no. Because it doesn't matter what the reaction order is, equilibrium will be established. So it just depends. Reaction order matters in terms of how quickly equilibrium is reached, but it does not matter in terms of concentrations at equilibrium. Does that make sense? Right, reaction order depends on how fast a reaction happens. So if the reaction is happening faster, equilibrium gets reached faster because we can go and change those concentrations more quickly. That relates to equilibrium, but it doesn't affect like what those concentrations are at equilibrium. Does that make sense?
Yeah.
Okay. Good questions though. Okay. So that's K, that's our equilibrium constant. This tells us these are 4 equilibrium conditions. Okay, so this because K can only be written and shown for equilibrium. If K is greater than 1, what does that mean? What's bigger, the numerator or the denominator? The numerator is bigger. So if the numerator is bigger, what do you have more of? You have more products. So that means that your reaction is product favored. If you have 1, right, greater than 1 is, yes, product favored, but it has to be like over 100 for it to be product favored. If it's anywhere from 0.01 to 1, they're pretty equal, just as a reference. Once you get over 100 and you start using scientific notation, then that's when it like matters product favored or reactant favored. So then if K is less than 1, what's bigger? This time, the reactant, the denominator is bigger. So denominator is bigger. You have more reactants, which means you are reactant favored. So then I'll say, if you have 0.01 to K to 100, you have equal amounts of products and reactants. There's just not too much of a difference between that when you have that small numbers, because you'll see K values that are like times 10 to the 10th for K, right? Very product favored. But then you'll see K values that are times 10 to the negative 27th, right? Very reactant favored. So between 0.01 and 100, you have pretty equal amounts of reactants and products.
But if they're at equilibrium.
Yep.
Why is it important to know whether or not it's reactant or product favored?
Because equilibrium is just saying that the forward and reverse rates are equal. It does not mean that their concentrations of the reactants are equal to the concentrations of the products. We just want to know when equilibrium is established, when the chemistry is over, in a sense, do we have more reactants? Do we have more products? Does that make sense? Right? Because if this reaction up here, if we're forming ammonia, but it's reactant favored, that means that we need a lot more of our reactants in order to make enough ammonia for us to use, kind of situation. Right, in my research setting, right, I have 2 DNA molecules. I need to make sure that I favor the product side of forming the hybridization of my 2 DNAs, right? So I need to make a reaction or do something to my equilibrium that favors the product side. So I get more of that double-stranded rather than the 2 single strands.
How does that play into like spontaneity?
Spontaneity, you'll get to that in a little bit. You'll see how K and Q are related to delta G.
Because if one side, because I'm thinking right now, it's like if one side's more is spontaneous in one direction, it's not in the other. How come they're both occurring at the same time?
Yep. So, and that just plays into like energies and stuff. But you'll see that one is spontaneous in the forward direction, one is not spontaneous. And delta G therefore favors, and because of that, delta G will favor the reactants or the products. There's a whole equation that relates to it, and you're like, oh, it all makes sense. And then you can solve for delta H and then delta S and then delta G, and then you can solve for K, and everything's great.
She also mentioned that you can't measure K or Q in solids.
Correct.
What's the reason behind that?
That concentration is not changing. So if you have something where, or if you consider a beaker, that amount of liquid you have is not changing. So liquids don't count towards K or Q because you will keep that certain volume that you have. If you have a solid in there, that will stay as the solid. It's not going to change its concentration going back and forth. So that doesn't contribute to the concentrations of everything else going on.
You said liquids don't either?
Liquids don't either. It has to be either aqueous or gaseous.
Then what about like when water decomposes like hydroxide, H plus?
Yep. So then you just focus on the hydroxide and H plus ions. Nope. So if you have H2O liquid, this breaks down into H3O plus and OH minus. I guess H plus. Right. Those are both aqueous. So K here is just H plus times OH minus. you'll see this work itself out more once you start talking about acids and bases, and you'll see what's actually happening with all of that. Right, because usually you have water by itself, and so it's feeding off of itself. So you'll see that more just in a couple lectures. We'll get a little bit more acid-base chemistry. Yep. Thank y'all. Yeah. Okay. Thanks for coming, y'all. If you have any other questions, just let me know. I'm here until the next class. So
Do you have any like recommendations for like study chapters?